Let's dive a bit deeper into the science behind electrolysis. By passing a direct electric current through a substance, it will suffer certain chemical changes. These changes are driven by chemical reactions that wouldn't otherwise occur. By applying a direct current, water is decomposed into oxygen and hydrogen gas. Hydrogen will appear at the cathode, where electrons enter the water, and oxygen will appear at the anode. The amount of hydrogen generated is twice the amount of oxygen, and both are proportional to the total electrical charge conducted by the solution. This is sometimes called water splitting, and it's one of the methods used for extracting hydrogen, accounting for around 5% of the global hydrogen production. Hydrogen gas released in this way can be used as hydrogen fuel, a zero-carbon fuel burned with oxygen. Alternatively, it can be remixed with the produced oxygen to create oxyhydrogen gas, commonly used in welding and rocket fuel. If the reaction rate is controlled, such as to release its energy in the form of electric current as opposed to heat, hydrogen may also be used for storing energy. When hydrogen is consumed in a fuel cell, it releases energy and produces water by recombining with the oxygen. This way, energy can easily be stored, moved, and delivered from other sources. This is why hydrogen is an increasingly attractive fuel option for transportation and electricity generation applications. But extracting hydrogen is not the only application of water electrolysis. On the International Space Station, oxygen for the crew is produced through an onboard electrolysis system. The system, installed in 2006, is capable of supplying oxygen at ambient pressure with 80% efficiency. The basic electrochemical experimental setup is composed of two electrodes submerged in an electrolyte solution, which serves as an ion conductor. The system can either produce or consume energy, meaning that the observed phenomena are reversible. First, let's establish some terminology. In the experimental setup, we designate a working electrode and a counter-electrode. The former serves as the electrode of study, and the latter completes the circuit and allows for the flow of current. We also need to introduce the notion of interface, that is, the surface of interaction between the electrodes and the electrolyte solution. Now, in order to have consistency in our measurements and observations, we also need a convention. The electrode at whose interface the reduction reaction occurs we call cathode, and the one where the oxidation occurs we call anode. This also hints at the fact that the type of reaction that we will observe is a reduction-oxidation reaction, or redox. We need a power supply that allows us to see and control the voltage applied on the system. We also need a multimeter in order to measure the voltage. We'll use a simple beaker in which we'll place the graphite electrodes. What we are interested in for the material of our electrodes is, first of all, chemical neutrality with respect to the compounds of our solution. Moreover, a high surface area increases the overall area of the interfaces, which will in turn increase the efficiency and rate of reaction. We make the electrolyte using salt and distilled water. The voltage applied will split the salt into sodium and chlorine ions, which will facilitate the flow of current. We know that a saturated solution at room temperature is 23% by weight, but for this experiment we will make a 5% solution. For this, we dissolve 15 grams of salt in 285 milliliters of distilled water. We now place the electrodes in water and connect them to the power source and the multimeter. We turn on the power source and start applying a potential. We slowly increase the voltage until we can see bubbles forming at the interfaces of the two electrodes. This is called the decomposition voltage, as it is the voltage at which the molecules start to split. Inside the electrolyte, the positive hydrogen ions are attracted to the cathode and the negative oxygen ions are attracted to the anode. When the hydrogen and oxygen ions meet the electrodes, they gain or lose electrons respectively. They become neutral and form molecules with themselves. These molecules cluster together to form the gas bubbles we see. You can see that we added a third electrode in our system. This is a reference electrode, which is an electrode that has a stable and well-known potential. We use this reference electrode because it allows for control and measurement of the voltage applied on the working electrode. We observe a potential difference of 2.49 volts between the reference and working electrodes. Once we have a non-negligible concentration of reaction products, that is, hydrogen and oxygen at the electrodes, and no voltage is applied, we observe a difference in potential between the electrodes. This has the opposite sign of the previously applied voltage, and it can also be seen with respect to the reference electrode. This is because the oxygen and hydrogen ions are recombining to form water molecules. In the next part, we will study in greater detail all the phenomena presented here. Thank you for watching!